Hi, my name is Saurav Behera, and this is my Physics 2211 Lab 3. Before I go into the computational models for the lab, let me go over some key ideas. Newton's second law and the momentum principle are used to calculate the net force acting on the star in the computational model of a star orbiting a black hole. We can use Newton's second law, which is F net equals dp over dt, to use the star's motion to help find the net force of the black hole acting on the star without initially knowing its mass component. Additionally, since gravity is the only force we are considering acting on the star in this scenario, F net can be set equal to F grav, in which the mass of the black hole can be found with the equation provided at the bottom. The initial conditions I set for the computational model are the gravitational constant g, the mass of the star, which is provided as 2 times 10 to the 30 kilograms, and the time interval taken in between data points as 86,400 seconds, which is equivalent to once a day. On my screenshot towards the right, my calculations using Newton's second law are shown. I calculated the initial and final velocity, for which I used to calculate the initial and final momentum. This allowed me to calculate dp dt and use that value to approximate F net. Using vector calculations, I was also able to find the parallel and perpendicular components of F net. My bottom screenshot shows the code I used to calculate the average mass of the black hole given all the values the program returns for its mass. For each iteration, I summed up the masses of the black hole and created a counter so that at the end, I could divide the total mass by the number of iterations to find the average mass. Here is a video of the model in action, and at the end, it provides a value of the F net, its parallel and perpendicular components, as well as the average mass of the black hole. For my second computational model, we are trying to launch a spaceship off of a planet orbiting the black hole, and to fly around the black hole without crashing into it or the planet we launched off of. I chose a speed for the ship's initial velocity to be 1 e6 meters per second in the x direction and 3 e6 meters per second in the y direction. In the iteration loop, we calculate the net force of the black hole on the planet and the spaceship every second, and we use Newton's universal law of gravitation to solve that. To model the planet's and the spaceship's movement, we use Newton's second law to constantly update the changing of each respective position and velocity. So here is a quick video of the model in action, and the orbit in the purple is the spaceship and the orbit in the blue is the planet. In this lab, we were also asked to explore some additional questions pertaining to the topics we were exploring. First, what is the difference between net force and its parallel and perpendicular components versus the rate of change of a momentum and its parallel and perpendicular components? The answer is there are none. Net force is the rate of change of momentum, so the question is redundant, because they are the same mathematically. However, instead of treating force as the product of mass and acceleration, it helps to think of it as a rate of change of momentum problem, in this instance, when the mass of the black hole is unknown, simply by observing the kinematics of the elements of the system. If we wanted to enter into an orbit around the black hole, we would consider the object to be traveling in circular motion around the black hole due to the black hole's force of gravity. Thus, force of gravity on the spaceship due to the black hole acts as a centripetal force. We can set those two equal to each other to find the initial velocity needed for the spaceship to enter into orbit.